So up next, we're going to have a delightful talk on the other kind of CAD, as in 3D CAD, from Dan. I hear he's from a great university, University of Washington. And with that, we'll go ahead and hand it away. Hand it over to Dan, sorry.
All right. So I'm here to talk to you a little bit today about referencing in computer-aided design. So we're talking about 3D shapes. So let's look a little bit at how CAD is used today. So CAD, as you may or may not know, is secretly a program. So engineers model 3D objects, basically everything around you, as a little mini program. And the reason that they do this is because it's very convenient to edit when you make design changes. So here we're modeling a mug, we have it in 2D, we make it into a 3D shape. And if we want to change the height of the mug, we might go in and we might change this little height parameter, and now we get a taller mug. And everything is great because the program has taken care of regenerating all of where the edges and vertices and how things should curve so that we can get a taller mug for free. Everything's great, everything's taken care of. So because we have a program, we can actually do a lot more than just regenerate one object for free. The program is implicitly defining a space of many possible objects that we could be generating, and it would be nice if we could look through this whole space and do optimizations and find things like, oh, let's get the strongest bridge or the lightest plane. And it would be really great if we could do this, but unfortunately, because CAD systems are designed to model single objects, they assume that there is a programmer there in the loop. Every time the parameter changes, the CAD system assumes that somebody is there looking at it, making sure that, yeah, this was the right thing. Because modern CAD has optimized for this use case, and is not yet optimized for the use case of designing many objects. In fact, it contains many semantic issues with respect to what we're going to call references. So what are references? The way that parametric CAD is done typically is modeled as a sequence of operations, and because this is all in a GUI, users will make a rectangle and then they will click on the rectangle to extrude it. Then they will take a face of that and they will click on the face and they will put a hole in it. Then they will take an edge and they will click on the edge and they will round it off. So at every point here, the user is implicitly making a selection, and the sort of CAD system traces what they did and will reapply that when something changes upstream. And this is really great if you are a user that wants to not think about this as a program and you just want to kind of get things done. Click, go, easy. And referencing is really useful when designing these programs, particularly because it allows you to reuse geometric logic. So imagine you had to place all of your objects globally in the right place next to each other, and you couldn't just click on something and reuse that value. Then you would have to do a lot more math, right? If you intersected a square and a cube, that's some complicated function, and you want to place something relative to that. You want to have easier relative positioning. And it allows more operations to be encapsulated. So this idea of rounding off an edge, we would like the CAD system to be able to do this for us. We don't have to redo this operation, place elements globally next to each other all the time. So referencing is good. However, referencing is also pretty hard. Remember when we were changing parameters upstream, we get a taller mug? So in these cases, we take the radius of a circle here on the left, and we make that circle larger. And since we're subtracting, now that circle actually becomes 2 curves instead of 1 curve. And we still want to round off the edges of that circle, but the reference has subtly changed. Same case on the right. We have one edge that we want to refer to trim off, but as we make the trim of the corner there a little bit smaller, the context of the shape around it changes. We have a different number of edges and faces and vertices, and we would like our references to be able to track through such topological changes in the shape. So what is a reference actually? If we look at a simple program in 2D, this sort of captured the essence of what we're trying to do. So imagine that we have 2 squares and we're subtracting 1 square from the other, and we would like to find a point, particularly on the intersection of that, and get the point on the subtraction. So we want to select this point from C. And note that there may be many points, right? Depending on how the squares intersect, they could intersect in different ways. B could completely swallow A, and there could be no points. So one very naive approach would be, let's select it by the index, get the first one. Depending on how they intersect, this might or might not be correct. slightly more intelligent, we can say, okay, well, let's take the closest point to a search point Q, where we can say, oh, sort all of the other points and get me the one that's closest. And this is better, right? It's more robust to some things, but it's kicking the can down the road. Now we need an equation for where this point Q might be, and we need to make sure that really, is this the point that we want? And really, it involves just as much programmer effort to move the squares around. We can delegate the problem entirely to the programmer and say, okay, it's your problem, write some code that searches over this whole data structure and gets you the right thing, but we'd like to be able to do a little better than that in terms of usability. So modern CAD systems actually solve this problem using heuristics. And you can tell from the title of this slide that this is going to go really well. So the problem with heuristics, of course, is that they work really, really great when they work and really, really poorly when they don't. So here we have some instances of magic happening in CAD. So we're rounding off 2 corners at the top of this object. But as we change the height of the object, we will see that suddenly there becomes a point at which different corners start being rounded off, because the CAD system has intelligently decided that, oh, the corners that you wanted to trim disappeared, so I will trim different corners, and now we're suddenly adding material instead of subtracting it. So we expect there not to be these interior corners, and suddenly there are. In another example, so this is given from a widely used CAD system called Onshape, which you can try out in your browser. So here I have some shapes being subtracted to make a little slot. And I will go into the slot and attempt to edit it and change one of the rectangles. I'm going to make it a little smaller, and I expect the slot to look like it does on the bottom right. And I see that, in fact, this doesn't happen, and the CAD system has charged forth. It has applied its heuristics, and now I end up with 3 shapes, and this shape is completely unfabricable, and I don't even have any errors, right? Because there's nothing geometrically that's preventing this from computing, but the CAD system has misapplied due to heuristics. So the problem here is that when we are specifying references on one particular object in one configuration, this is not enough information in order to be able to correctly generate this program across the many possible topologies that it should be able to represent. So what is the solution, you may ask? Well, we're at a PL conference, so it is a language for specifying your intent across these different configurations. So how do we make such a language that's also easy to use? The key insight is that when we have these different topologies, things aren't happening randomly or arbitrarily. In fact, we have a program that generates these things, and we can understand that in each operation, there is a correspondence between that operation's inputs and that operation's outputs. So we actually will take a look at a couple of different types of correspondences here. All right, so we might subtract squares A and B to create this little L-shaped C. And we will note that all of the edges on C are actually subsets of either an edge on A or an edge on B, right? It's a sub-edge of the same edge in the same position. All right. If we were rotating A to create B, there's also a natural correspondence there. We're transforming it. Nothing in the topology there has changed. There's an easy bijective mapping between the edges of A and the edges of B. The final case is when we actually create new geometry, right? So we extrude something or we trim off an edge. We have this new edge that has been created, and that edge, or that new edge that's created, is actually dependent on a couple of things in the input, but it's not dependent on everything, right? So there is a natural sort of correspondence of, oh, you trimmed off this corner, this new edge is in some sense derived from that corner and its neighboring edges. Right, so we can actually trace these correspondences across a series of operations that we execute while the program is running. All right, and here I've highlighted the different kinds of edges that you might get when you run a different operation, but there are many more than are strictly shown here. All right, so each operation that we have is instrumented to add these edges. So how do we make a language out of this? Well, the first thing that we do is we want to establish a predicate using this graph. For every element, we can use reachability in the graph to determine, okay, something about this element, right? Is it reachable from some place in its history? So The way that we do this is by defining a few different operators that will trace through the graph from higher upstream and determine if a given topological element, which this might be a vertex, an edge, a face, what have you, is reachable from the argument to that predicate. Right. So we have three primary ones, and these are from, derived from, and contains. So from follows two different kinds of edges, derived from follows all of the edges, and contains, if you are trying to evaluate reachability to, say, a square, contains will evaluate the predicate to all of the contents of that square, so edges, vertices. If anything inside the square matches, then contains will match. So how do we use this to actually make a language? Well, so we have this query operator here that will take a set that we don't know what's in the set, and it will filter out the elements of that set accordingly. So here we want to select our point P from before, so let's try a few queries. So here we try from B, and so we get the 3 points that are from the square B. And this isn't quite what we want, so let's try something else. Well, okay, let's try from A.right, the right edge of A, and we get these 2 points here, and those are from the right edge of A, but those are also not what we want. Fortunately, we can combine those two queries, and we can logically intersect those sets, and we can see that, okay, now we're getting the point P that we want. Right, so in this way, the graph reachability is serving as a stable identity for this element, and this is well defined over all the possible topologies the shape can have. Right, you will never randomly get behavior that doesn't correspond to this. And this works over the couple of different topologies, but what if we change B? What if there are now 2 points that come from, if we make B smaller, that come from the right edge of A and B? Well, we can change the query. So this is the essence of the user now has control over what happens in new topological areas. So here we are, instead of taking anything from B, we're taking points that just come from the top edge of B. All right, so in investigating a couple of examples, so abstracting it a little bit, we want to filter a set C with this query, and we are creating a new set C prime that has everything filtered. So if we do from, we are evaluating the query such that there is any reachability in the graph from any sub-element of E to little c. If we do contains from, we are evaluating reachability from any sub-element of E to any sub-element of little c. And we can compose these queries through arbitrary Boolean combinations. So this is all well and good, but what properties do we get out of doing it this way? So we prove in our paper that you can select any element on any configuration, and this allows you to do nice things like we have user control over different topologies. So if we have an edge E1 selected in one configuration and we change the program so that edge is now split into 2, we can select either E2 and E3 or both or neither and so forth. One other property is that of smoothness. So we know that CAD programs, because the topology is changing, they're already inherently discontinuous, but we don't want to introduce additional discontinuities as a result of that. So when we are evaluating, say, by a distance-based metric, that might not work, right? So if we are evaluating the closest edge to this blue point, depending on how we rotate the square, that might change, right? The final property that we care about is being able to disallow various classes of program, right? So from before, when the shape split into 3 different elements, we didn't want to allow that configuration, and this is very important when an automated sort of algorithm is searching the space of design. So we would like to provide some user intent by saying, by ensuring that there is a query that will return a different result on different topologies so that the users can outlaw classes of topologies and assert that certain properties are true about their design. We evaluate our solution by creating a variety of different benchmark programs on a simple 2.5D CAD engine. And this means just that you can make shapes and add them and subtract them in 2D and then bring them into 3D and position them relative to each other. So in our paper, we showed that the overhead is relatively minimal compared to the costs of the geometric operations themselves, and that users were able to sort of interactively debug these queries by seeing their results, evaluating them on different sets as the program executes. So you could take the same query and evaluate it in multiple different places and see what edges you are getting. So our implementation is available on the web. You can try it out. And what have we done here? So with the ability to robustly specify these references, CAD can now begin to achieve some of its promise of high-level design change. And in turn, this enables this sort of automated exploration of design spaces. It enables synthesizing programs whose topology changes from data. It enables verification that the queries are actually correctly written, and much more, unifying PL and design. Thank you.
Great, so we have the mic here in the center and also the Discord up. One thing I was curious about is to what degree, like what properties of the representation do you depend on? So, mentally I'm imagining a mesh in this case. Does everything still work out if I use signed distance fields or B-reps, or like what do you need from the underlying topology to have this referencing scheme work?
Yeah. So this scheme is designed to work specifically with what we call explicit representations, where there is an object in memory that is the edge or the vertex or something like this. With a signed distance field, everything is implicit, right? So there's not really a particular corner there. So you would have to find some way to represent that corner in memory, whether it's another function or something like that, in order for the scheme to work.
Hey, Gus Smith from the University of Washington. Dan, thanks for the talk. This is awesome. I'm wondering if you've thought at all about how the core ideas here could be moved to completely different domains. So one thought that I had while watching this is it sounds a lot like you could use this potentially for example, trying to trace how a scheduling language makes changes on a lower level language, as you add scheduling transformations. But I'm wondering if you've thought about that as you were doing this project.
Yeah, so we see this as a particular instantiation of a more general pattern, which is being able to hold this stable pointer into a data structure as it's changing over a variety of different transformations. So this is exactly the same kind of thing. So imagine you have an optimizing metaprogram or something like that that is moving around your objects differently, and you want to point to some different sub-program and say, okay, this is the same one over here. You could instrument all of your transformations in a similar way and enable similar querying to take place in order to hold these stable identities.
One more question from me. I really love this paper. I think it's just beautiful. So you mentioned how everything can be uniquely referenced. And I guess from that proof, do I get an algorithm out of it? Like in the UI, when I click on something, can I get like a list of possible queries I could choose from to pick what I meant for that instance?
Wow, you've correctly identified future work. Yes. So you do get, the proof is constructive, so you do get an algorithm for selecting something, but it's not necessarily super general. So you will get an algorithm for selecting it on that one topology, but as you kind of change topologies, it's not guaranteed that you'll get what you want, because that would involve reading the programmer's mind, and as of yet, we are unable to do that.
That's the LLM's job in the future, right? Okay, let's thank Dan again.